All right. Hello, everyone, and welcome to the third and final part of the Waves Optics and Modern Physics course. Let's set the dial back to the end of the 19th century. By this point, most of what we could see with our own eyes was figured out. Huygens explained diffraction. Thomas Young and his double slit experiment show the interference pattern, proving that at the very least light could behave like a wave. Boltzmann explained thermodynamics, Newton figured out gravity, and Maxwell unified electricity and magnetism. The 19th century basically brushed its hands together and said, well, that about does it for physics. Then the 20th century showed up and said, allow me to introduce myself. In the 20th century, we had the rise of quantum mechanics, of relativity, of special relativity, of the light wave particle duality. We had Heisenberg, Schrödinger, Planck, Einstein, and so many more. The quantum theory and the theory of relativity set the stage for the modern world of physics. Much of what is studied now can be done thanks to our understanding of relativity, including the field of cosmology and GPS devices, actually. Beyond this point in the course, we'll explore a world of physics that we don't see every day. Before, and in other classes, we were really just working with classical physics, which explains what we see in our everyday lives pretty well. But now we'll see that when things start to move near the speed of light, or when things are really, really small, classical physics is not enough to explain what's going on. But sometimes relativity is the answer. If we're going to talk about relativity, the fact that events happen relative to some frame of reference, we need to establish that anytime we're witnessing something happening, some event happening, we are observing that from a point of view, from a frame of reference. Whether it's just you standing in front of your computer screen or sitting on the couch, or your friend on a plane, a man on a train, or Hercule Poirot from Agatha Christie's detective novels in his trusty automobile, people in different frames can all be observers of a physical event. And let's establish that these frames are inertial. That just means that they're not accelerated. So if you're a non-inertial frame, that means that you won't see anything accelerate unless there's an external force. So if you're like standing in a merry-go-round, that is not an inertial frame. You see things spinning. So we have a principle of Galilean relativity, which is sort of a principle that reflects on what we learned, in physics so far, that the laws of mechanics must be the same in all inertial frames of reference. That just means that in your inertial frame of the plane or the train, the automobile, or a bird on a tree, or you on the chair, you will all agree that the laws of mechanics are acting as they should, as you all witness the same event from your respective frames. This means that there's no correct frame, exactly. This means that your observations of an event in an inertial frame are just as valid as someone else's observation in some other inertial frame. So let's talk about that. Let's consider a situation where there's two different frames and some things are different. You have two observers. One is standing on a moving truck and they're tossing the ball up in the air. So this observer is on the frame of the truck, and from their point of view, the ball gets tossed up and falls back down into their hand. The second observer is their friend on the ground. They are, seeing the first observer, the car moving relative to them. They're seeing the car moving to the right. They also see that as their friend, the first observer, tosses the ball up into the air, the ball moves up and then down, but also because the ball was moving with the truck, the ball also displaces to the right. So overall, the path of the ball, as seen by someone standing on the ground, is a parabola, while somebody standing on the truck, like the person who threw the ball, is just the ball going up then back down. So which one of these two is correct about the path of the ball? Is the observer right that the ball just went off his hand and fell back down? Is the observer correct that the ball is making a parabolic motion as it goes up from the hand and back down again? Or are they both right? So Galilean relativity says that laws of physics are the same across all frames, implying that all frames are equally valid. So they're both correct. From their relative frames, one sees one type of motion and another sees another type of motion while they are on the ground. So despite the fact that the path looks different to each observer, they both agree that all laws of physics are in place. They agree that the law of gravitation is there, conservation of energy is there, and so on. Also, when you talk about different frames, you all have your own coordinate systems since it depends on where you are relative to some event happening. So, for example, consider two frames S and S prime, each one with an observer O and O prime. And the difference between the two frames is that the frame S prime corresponding to observer O prime is moving to the right relative to the first observer. So if we were also standing on the ground next to the first observer, we'd see the second one skating away to the right. Now, some event happens, perhaps lightning strikes, and both of these observers are going to write down the location and time of the event. The first observer writes down the full coordinates using an XYZ system and also writes down the time. The second observer, since they have skated away, they're at some distance closer to the event actually, they're going to write down their own coordinates for where the event happened, and they're going to be different. Just generally, we're going to call that coordinate system x prime, y prime, and z prime, and he'll write down the time t prime. So for example, where I'm standing, the Montreal cross is, I'd say, 5 kilometers away from me, from my frame of reference. But from somebody on the west end of the island, the Montreal cross will be many, many, many more kilometers away than that. So on different frames, or idea of where something is located relative to us is obviously going to be different. So how do we transform the coordinates of one frame to another? In the case where the frame S prime here is moving to the right, then the only difference in the coordinates is just the horizontal coordinate x and x prime. So we just have to account for the fact that the moving frame kind of gets closer to the event. So the x coordinate in the moving frame, x prime, is probably going to be smaller than x in the Earth frame where O is standing. Now, the vertical location of the event, the y and z position of the events are the same for both observers, since the only difference between them is the horizontal speed of one frame. And also, both observers would agree that the event happened at the same time. So whether I'm standing by the Montreal Cross and somebody's standing below the mountain, if we both see lightning strike the cross, we will both agree that it happened at the same time. Except that one would say that it happened closer to them. So what if there's a moving object? If you're standing on the ground while your friend's skating away, you notice that there's some tennis ball moving with some speed. Let's call it ux. What about the observer? What about the person in a moving frame? What speed do they measure? So clearly, this ball and the second observer are both moving to the right. So the relative speed there would be the actual speed of the ball minus the speed of the moving frame. So say you see the ball, you're standing on the ground and you see the ball move at 10 meters per second, your friend's skating at 1 meter per second. From their point of view, the ball's moving at 9 meters per second. So consider this. A baseball pitcher can throw a 90 mile per hour fastball, and right now they're standing on a railroad flat car moving at 110 miles per hour. They throw their fastball in the same direction as the velocity of the train they're on. Using the Galilean velocity transformation equation that we just saw, what is the speed of the ball relative to the Earth? So what we actually know here is that the man is throwing a ball in the moving frame. So we know that in the moving frame, the ball is 90 miles per hour, and we actually need to find what the ball speed would be as seen on the ground frame. So we're looking for this term here. So we can do some algebra, and we can then take this term to the other side. So we're going to take the speed of the ball thrown within the moving frame plus the speed of that frame, and that way we'll get the speed of the ball as seen by someone standing on the ground. So the flat car is moving at 110 miles per hour. The ball is thrown in the same direction at 90 miles per hour. So you add them together and you get 200 miles per hour. Okay. So here's the thing. We're coming up to the end of the 19th century, and Maxwell did an amazing job by consolidating electricity and magnetism with his 4 famous formulas. However, part of his theory implies, or at least requires, there to be a constant speed of light, regardless of what inertial frame you're on. So there's a demand to have some frame where the speed of light is constant. And by the way, the notion of speed of light generally refers to the speed of light in free space, which is 3 times 10 to the 8 meters per second. And the shorthand for that is the letter c. So rather than trying to throw away Galilean relativity and think of something else that can satisfy this idea of light speed being constant when we expect that all speeds are always relative to your frame of reference, they thought that they could maybe marry both ideas by hypothesizing a new medium called the ether, which basically permeates the whole universe. The whole universe is covered in this ether that carries light by some kind of ether wind. And in that ether, light does in fact move at the speed of c if you were measuring it from a frame at rest with respect to the ether. In other words, if you were just swimming in the ether wind, just coasting along, then you'd see light moving at the speed of c. And if you're just in any other frame of reference, then you would measure the speed of light. Depending, the speed of light you measure will depend on, again, the motion of the frame you're on. So this allows you to have this exclusive ether frame that complies with Maxwell's implication of a constant speed of light, and still allows for measurements of speed of light to change depending on the motion of your frame of reference. So the idea overall is that light is carried by this ether wind, and there's a particular direction that the wind blows through the Earth. So assuming, let's say that the speed of this ether wind as measured by the Earth is just some speed vector v, and as ever on Earth, you would then be able to measure the speed of light, observe the speed of light with different values depending on the direction that the wind is blowing on that particular day, or on the orientation of the Earth with respect to the wind. If light's moving the same way as the wind, then an observer on Earth would measure a speed of light bigger than c. If the speed of light one day is coming towards you, but it's blowing against the wind of the ether, then you would measure a lower value than c because the relative speed would be smaller. And then, right, there's a case where the angle is not perpendicular or parallel, it's just something else. So the speed of light would be something else entirely. But either way, it just meant that with existence of an ether, you would end up measuring different values of the speed of light at different points, depending on how light is being shown through and what direction this ether wind is blowing. So, how do you prove this? Well, to explain that light is moving in an ether, the scientists known as A. Michelson and Edward Morley conducted a series of experiments using interferometry. So the basis of interferometry is you shoot one coherent light source into a mirror, and it's kind of like a mirror lens situation where you have essentially a beam splitter in the middle that's going to send one light beam towards one mirror and another light beam towards a second mirror, and they'll converge and the beam splitter back in the center and move towards a telescope where you'll be able to observe the recombination of the two mirrors. Now, it's worth pointing out then that the general experiment for interferometry, you basically have two beams. So the laser light goes into the beam splitter. You have beam one here and beam two, and what you can alter is you can change the length of each arm, and in doing so, you would then alter the path length that the beams travel to get to you to get to the telescope, and in doing so, that creates an interference pattern. Now, another way that the interference pattern could be created is with the ether. Suppose that the arm lengths are actually the same, so that means that the path difference wouldn't be significantly big. It would probably be a path difference of 0 if the distance here and here are the same. But if the ether wind exists and it's there, it will mean that you could align it so that the ether wind blows through light on one of the arms, but it doesn't blow, it blows perpendicular to light on the other arm. So in other words, the speed of light moving through arm 1 will be different than the speed of light moving through arm 2. And this difference in speeds would cause them to arrive at the telescope at a different phase. And so it will cause interference, and you'll be seeing a interference pattern occur since, again, one arm, the light going through one arm is kind of boosted by the ether wind while the other one really isn't. And what then you could do is you're now seeing this interference pattern, these fringes from the two beams, one kind of being boosted by the ether wind. Now, they thought, let's rotate the device by 90 degrees so that arm 1 is now facing the ether wind and arm 2 is not. In doing so, this would cause a shift in the interference pattern because now you'd be changing which light beam gets the ether wind boost. So you'd expect the fringes to move a little bit. That did not happen. Rotating the interferometer 90 degrees or any other angle, or making the arms longer and longer for better sensitivity on how much the fringes could potentially shift, did not make a difference. No shift was ever seen in the interference pattern in the telescope. So that must mean that the idea of an ether wind is not, at least not testable, at least not, you cannot demonstrate an ether wind with this experiment. And many follow-up experiments were also failed to show the existence of any ether wind. And now we know that light doesn't need a medium to travel. Light is a form of electromagnetic radiation that can travel in a vacuum. We have left behind the notion of the ether, and we will also have to leave behind the principles of Galilean relativity if we wanted to understand the speed of light better. So at this point in history, near the end of the 19th century, we have to start new. We had to adopt a new principle of relativity. That's all for now, and I hope you join me next time.